So, uh, is it okay? Okay.
Yeah,
Okay,
I think
yeah.
you can make
Then
it bigger on my end.
then we can start. So welcome everyone to this special session of the NCTS Algebraic Geometry Seminar. So today we're very happy to have Benjamin Becker from the University of Illinois, Chicago, and he is going to talk to us about the Bailey-Borel compactifications of period images and the B semi-ampleness conjecture. So yeah, please start.
Perfect. Thank you. Thanks so much for the introduction and the invitation. It's a pleasure to speak. And um, yeah, I'm looking forward to being there actually in a few months. So this talk is um, uh, definitely these are the slides for an hour-long talk. So you should definitely ask me questions so that it would becomes an hour and a half long talk. So don't be shy about asking questions. Also, well, okay, I don't know if this is useful to anyone, but let me put in the chat. Here's like a handout version of the slides I'm using in case you wanted to like flip through and want to go back to something. Okay, great. Anyway, okay, so let's get started. So I want to start off by just reminding everyone of the classical story of the sort of the first Bailey-Burrell compactification there ever was, and that is of the moduli space of principally polarized abelian varieties. Let me see if I get my pointer. Okay, perfect. Yeah. Um, so this space starts off life as a complex analytic variety. We take the sort of Siegel upper half plane, which parameterizes lattices in a complex vector space that admit a principal polarization. And we take the quotient by the properly discontinuous action by the symplectic group, acting essentially by Mobius transformations. That gives us some complex manifold, or really an orbifold, because there are some points with stabilizers. And this story starts with the work of Satake in 56, where he provided a topological compactification of the space. So the space, this complex manifold, is non-compact, and you can add. So you can take AG, which is just this space, and add in all the smaller ones. So AG minus one is the sort of topological space of principally polarized G minus one dimensional abelian varieties, and then G minus two, and so on and so forth, down to A1, which is just the modular curve parameterizing elliptic curves, and then A0, which is just a point. And you can topologize this so it's a nice compact topological space. Now, he also suggested that this topological space ought to be the topological space underlying a compact complex analytic variety, which would then be a complex analytic compactification of AG. Okay, so this was proven a couple years later by Bailey, who actually did slightly more. He showed that not only was this topological space, not only can you equip it with the structure of a complex analytic variety, which agrees with the complex manifold structure on the open part on AG, but it in fact has the structure of a projective algebraic variety. And in fact, you can realize this projective algebraic variety as proj of a graded ring of automorphic forms. Okay, so this were sort of well-studied analytic objects, certain kinds of functions with certain transformation rules on the Siegel upper half plane. And you form the graded ring of such automorphic forms, and they turn out to give you a finitely generated ring, and you take proj of it. It gives you some projective algebraic variety, which contains as an open set this analytic quotient, and the boundary that you add is exactly these sort of smaller dimensional spaces that Satake added. Okay, so that's great. Um, and well, okay, so if you're coming from sort of the from algebraic geometry and you think of AG as the moduli space of principally polarized abelian varieties, when someone gives you a compactification, the first thing you want to do is understand sort of geometrically what the boundary is doing, like from a moduli perspective. And there is indeed a moduli perspective. It's a little too singular to have a universal family, but the points you're adding in the boundary do have a modular interpretation. And let me just describe what that is. So it has a sort of interpretation in terms of one parameter families. Okay, so this is my notation. Z over C is going to be some family of principally polarized abelian varieties over a curve C. Sorry, scratch that. I meant take C naught to be a curve minus a point. Okay, so it's like a punctured curve. And Z circle over C circle is my family of nice smooth abelian varieties. And I want to take a compactification of that curve by adding a point, and I want to take a compactification of the family that's semi-stable. Okay. So for instance, if we were talking about elliptic curves, you would want something that, where is this? That generically looks like a smooth elliptic curve, and at the singular fiber is acquiring a nodal singularity. Okay, that's the sort of semi-stable fiber I want to allow here. Okay, so this is a family of abelian varieties here. This compactification, I'm saying taking a semi-stable neuron model. I'm being a little loose here. These don't always exist. Maybe you have to take a finite base change, but let's ignore that for now. The special fiber, this Z naught, it turns out the smooth locus of it has a natural structure of a group variety, a commutative group variety, and its identity component is the semi-abelian variety. And any semi-abelian variety is an extension of an abelian variety by a torus. Okay, and so the compact part of that semi-abelian variety is the limiting point in the boundary, because the compact part of that Z naught is some abelian variety of smaller dimension. It turns out it's principally polarized, and that's just the point that we send it to, whatever the dimension of that is. We take, say if it has dimension h, then AH shows up here, and that's the point that we limit to. Okay, so this is a very clean, very canonical interpretation of what limit points are for one parameter families of abelian varieties. Okay, so any questions about that? Okay, cool. So there's also a natural polarization on this on this compactification. Uh, Somehow we're already seeing that here because we're writing it as proj of something, so it comes with an ample line bundle. But that polarization has an interpretation in terms of families of abelian varieties. So if we consider, now I'm going to let Z over AG be my universal family of principally polarized abelian varieties. There's a line bundle I can form, which is push forward relative one forms. So that's some vector bundle of dimension G. Take the determinant. Okay, so that's a line bundle. Let's call that L. It turns out this line bundle is sections of this line bundle are exactly automorphic forms, sections with a certain behavior at infinity. And therefore, it's this line bundle that extends to this compactification, this Satake-Bailey-Borel compactification, maybe up to a power. I'm going to be a little loose with that.
Can I ask a
Uh,
silly question?
yeah, please do.
So how do we actually know the graded ring of automorphic forms is finitely generated?
Well, so in the usual story, so there's a couple ways to prove that, but in the usual story, that's an analytic result. I mean, you take the you take you know you take these analytic functions and you prove that they're actually how do you? I'm not sure how you prove analytically. I know the algebraic geometry proof after the fact. Once you know it's an algebraic variety, then you're a proper variety, and you know that it's it's the global sections of some line bundle. I don't remember how you prove it analytically, but I think you first prove it analytically. in the kind of historical story. Does that answer your question? It's not a very good answer.
No, that's sort of, yeah, no, that's good. Thanks. Yeah.
I think the answer is you'd have to do it analytically, and I don't know how to do that. I don't remember how to do that. But it might be well, anyway, let me not speculate how it's proven if I don't know. But there's some you have to do that analytically. Yeah, good question. Other questions? Okay, cool. Yeah. So anyway, so this line bundle that I just formed by taking this determinant, it turns out it extends. Not only does it extend to this compactification, but it extends as an ample line bundle. Okay, so that's the kind of fourth main point about this Satake-Bailey-Borel. And there's another important property, which is a sort of a universality property. Really, it should be called a minimality property. This compactification is somehow minimal among all compactifications you could take of AG. And what do I mean precisely by that? Oops. Well, okay, I wrote this diagram down. Let's walk through it. So suppose X is a smooth variety and D is an SNC divisor inside it. Maybe I even write that down. Yeah, so this is a log smooth pair. And just from now and forever, I'm going to call X circle the complement of D and X. And suppose I have a family of abelian varieties, principally polarized abelian varieties, over X naught. Okay, so that means I have a map from X naught to AG corresponding to that family of abelian varieties. The minimality property that this compactification satisfies is that the resulting map to AG that I get coming from that family of abelian varieties always compactifies over the SNC divisor as a map to this Satake-Bailey-Borel compactification. Not only that, so not only does it compactify over any SNC divisor, it compactifies in such a way that the pullback of the extension of this line bundle that we just talked about agrees with the natural way to extend the line bundle upstairs. Okay, so I have to say a few words about that. Do I put that here? No, I don't. Okay, so if you have a family of abelian varieties over the complement of an SNC divisor, there is a natural extension for this determinant of the relative push forward of the relative one forms line bundle, which essentially comes from taking a semi-stable model of the family of abelian varieties and taking relative log differentials and taking the push forward and then the determinant. That gives you some line bundle. That's the sort of natural extension, which I'm calling LX, of the line bundle that you get from having this family of abelian varieties over X naught. Okay, and so what I'm saying is not only does this map extend over the SNC boundary, but the two line bundles that you can sort of naturally cook up, one coming from this natural extension you can do over an SNC boundary, and the other coming from this property that the line bundle extends to the Satake-Bailey-Borel, they both agree. Okay, and that's actually just as important as the extension of the map itself. Okay, great. So that's kind of a mouthful, but these are essentially all the important properties of this Bailey-Borel compactification of AG. I will mention that there is kind of a stronger version of 5 so Borel proved this in 72, but he proved in fact a stronger version, which essentially immediately implies it. And that is you have this same kind of extension result in the analytic category. Namely, if you have any if X circle is now replaced by the complement in a polydisk of the coordinate hyperplanes, and suppose you have a family of abelian varieties over the polydisk minus the coordinate hyperplanes, then it automatically extends to a map from the whole polydisk and in such a way that the natural line bundle extension on the polydisk coming from looking at logarithmic differentials is naturally identified with the pullback line bundle from the extension on the Satake-Bailey-Borel. Okay, and that implies this result basically because by Gaga basically. If you can do it for every polydisk, then you can do it for a proper X, and then by Gaga you have to get an algebraic map. Okay, cool. So anyway, so those are all the basic. Do I have one more thing? Oh yeah, so this is sort of the basic story for AG. So so Satake's original work on the topological compactification in 56, he then extended to the case of arbitrary arithmetic locally symmetric varieties. So these are quotients of Hermitian bounded symmetric domains by arithmetic groups. So he produced a topological compactification of any such arithmetic locally symmetric variety. And then in 66, Bailey-Burrell proved in general that you have a canonical compactification with all these nice properties arising as the proj of a graded ring of automorphic forms. Okay? Okay, so that is all the classical story. Let me just pause for a second to let people absorb that or ask questions if they want to ask questions. Okay, cool. Okay, so now let's talk about period maps, which is going to be sort of the non-classical situation. Let's again take x comma d to be a log smooth proper pair. So x is just a smooth proper, you can even take projective variety, and d an S and C divisor. And I want to consider a smooth projective family over the complement of that log smooth divisor. Okay, so let's call it Z circle over X circle. And we can consider the local system, which in symbols is written this way, which is just recording the kth cohomology of the fibers as a local system. Okay, so this comes equipped with a polarizable Z variation of Hodge structures, which just means, do I say it? Yeah, so we don't have to get into the specifics of what variations of Hodge structures are. All you really need to know is that this structure means, in particular, that this local system, if I form the associated flat vector bundle, so that's a vector bundle with connection, just by taking the tensor with the sheaf of analytic functions, that comes with a filtration. Okay, and that filtration has to satisfy all sorts of nice properties, but that's the extra data that being a Z variation of Hodge structures buys you. So in terms of this family, these filtration pieces are giving you sort of de Rham cohomology classes of certain kinds of algebraic forms in the family. Okay, great. So I have this filtration in a vector space that's well determined up to monodromy. That's what a local system is. It's sort of a vector space up to monodromy. So I have a filtration in that vector space. So I get a map from X naught into blackboard D, which is some flag variety, mod gamma, where gamma is the action of the monodromy group. Okay. And this is kind of the classifying map for this variation of Hodge structures. Again, it's tracking how the filtration is moving with respect to the locally, but with respect to the flat structure, the flat vector space. And this is called a period map. Okay, now this period map, it's an old theorem of Griffiths going back to when this was first being developed in the late 60s, that this filtration actually moves, it's holomorphic. I mean, I guess the way I've set things up, it's by definition holomorphic, but that's sort of a theorem in this geometric case. But this is a holomorphic map to some kind of complex analytic space, this D mod gamma. Again, this D you should think of as just kind of an open subset of a flag variety, kind of like the upper half plane in P1, modulo some group that's kind of like SL2Z. Okay, so this is like upper half plane mod SL2Z, or I guess since we've already been talking about Siegel space, it's kind of like this, but not exactly. So it's some other open, some complex manifold modulo an arithmetic group action. You have this holomorphic map. Now, holomorphic maps to complex manifolds, even from algebraic varieties, are not particularly well behaved. But it turns out that the image of this map, its closure is a nice complex analytic subvariety of D mod gamma. Okay, this was proved by Griffiths. So the closure of this image, this curly Y, is an analytic subvariety. And Griffiths in his 1970 ICM address asked a number of questions about these period maps. So first, natural question, sort of, is this image inside of D mod gamma algebraic, right? Some natural complex analytic variety sitting inside of this moduli space of, this is like a moduli space of Hodge structures. This curly Y is parameterizing those Hodge structures that show up in this variation of Hodge structures. Is curly Y algebraic? Second, there's a natural line bundle floating around, which has curvature properties that suggest that it's oh, sorry, I'm getting ahead of myself. There's a natural line bundle floating around. It's called the Griffiths bundle, and it's, well, you have the filtration pieces. You know, again, this is kind of the moduli space, the classifying space of Hodge structures. So the filtration exists universally on D mod gamma as vector bundles. And so you can take the determinant of the tensor, the determinant of the filtration pieces. That gives you some some line bundle in D mod gamma. And you can ask if this is algebraic. And then finally, so this is what I'm sorry, not finally. The next this is what I was jumping the gun and saying. You would in fact expect this line bundle to be ample on curly Y if curly Y is algebraic, and that's because it has some positive curvature properties. And finally, if you admit all of that, then you could even ask whether there's some version of a Bailey-Burrell compactification of this curly Y. In other words, a compactification that satisfies all the properties that I spent the first 15 minutes describing. For instance, that has the sort of universality property with respect to this line bundle. You know, it's projective. This line bundle extends. It has this kind of modular interpretation, so on and so forth. Okay, so you can ask all these questions, and Griffiths did ask all these questions. All these questions are much more complicated in the in this situation because D mod gamma is, you know, unlike the case of let me just write it again just for emphasis. I said that this was like Ziegel's space modulo SP2GZ, but in fact it's very much not like it because you know, the whole point of the Bailey-Burrell compactification was that this quotient ends up being a quasi-projective algebraic variety. But in the general case, for a random smooth projective family, this D mod gamma, the space of Hodge structures, will certainly not be an algebraic variety. So that kind of complicates this whole story. Okay, so here's now the main theorem. And the main theorem, okay, well, there's a preamble to the main theorem. So first of all, these first two questions about curly Y being algebraic, this line bundle being algebraic, and it being ample, these were answered a while ago with Johan Brunebarb and Jacob Zimmermann. And basically, the answer to these two questions is yes. So in this diagram I drew here, basically this whole portion, like this map and this curly Y, is all algebraic. Okay. So this map, the closure of the image at the period map together with the map to it are all uniquely algebraic. So they're the analytification of some algebraic morphism. The line bundle is an algebraic line bundle, again, uniquely, and it's ample. Okay, so everything we asked for in questions A and B holds true. And then, so for this last question, that's the theorem I want to talk about today. So this is with, I should have said at the very beginning, this is all joint work with Stefano Filippazzi, Mirko Mauri, and Jacob Zimmermann. And there's going to be several, well, there'll be several theorems, but this is the, well, this is theorem one. So let me state it this way. So there is a graded ring I can form, which you should think of as like the graded ring of automorphic forms that showed up in the classical story. So I'm writing it in the following way. So you take powers of this line bundle, this Griffiths bundle, which by this theorem is algebraic. Okay, so Y is an algebraic variety. This is the image of this period map. Again, by this theorem, Y is algebraic, and this line bundle is algebraic. So I take sections of the powers. Of course, Y is a quasi-projective variety, so sections of a line bundle could be ginormous. So that's why I have this subscript mg. So these are the sections that have moderate growth. So this line bundle comes equipped with a natural Hodge metric floating around. So once I look at the moderate growth sections, this is now a finite dimensional space. Okay. And it's compatible with products, so I can put these together to get a graded ring, which is not clearly finally generated. And then the theorem is that that ring is finally generated. And if you take its proj, then that gives you a projective variety, which compactifies Y, and which has all the nice properties that we were talking about. Specifically, this line bundle extends amply and universally in the sense of property 5. So whenever you're in the log smooth situation, if you have a map to Y on the complement of a log smooth divisor, then the map to YBB will complete over the log smooth divisor in such a way that the line bundle, the extension of the line bundle down here will pull back to the natural extension upstairs. Okay, so I should say that just as with families of abelian varieties, there is a natural Hodge theoretic way to extend this Griffiths bundle that I'm talking about in the log smooth situation. So in Hodge theory, there's always kind of natural ways to extend the kind of various gadgets in the log smooth situation. And in fact, we even have this for the analytic case for 5 prime. Okay, so there's a couple of the 5 properties I mentioned at the beginning. Not all of them are clearly contained in this theorem, so let me spend a little bit of time explaining the other. So obviously 5 is here, and this finally generated ring is kind of like the ring of automorphic forms that appeared in 2, or maybe it was 1. So what about the other things? Let me say a few words about that. So, okay. So first, another way to state this, or at least a consequence of this, is the following. If you have a proper log smooth pair, so x comma d, where x is smooth and proper, and d is an SNZ divisor. Suppose you have a polarizable integral variation of Hodge structure. Again, if you want, you can just think of a smooth projective family over the complement of d. And you form this line bundle, then the conclusion is that it's semi-ample, right? And that's just because you can take the image of the period map, form this compactification, this line bundle extends amply, and then this map automatically, the map from x, let me write it. You have a map from x to that y, from x minus d to that y. So here, you have x minus d mapping to that y, and by this universality property, that map extends to this Bailey-Borel compactification in such a way that the pullback of the line bundle is the natural extension here, and that means it's the pullback of an ample bundle, so it's semi-ample. Okay, so this theorem is including within it some semi-ampleness results. Also, so something that was true about AG, about the Satake-Bailey-Borel compactification of AG, is that we knew exactly what we were adding in the boundary. We were adding AGs of smaller dimension, right? Because it was recording the compact part of the semi-stable neuron model. So in the same way, this Bailey-Borel compactification is stratified by subvarieties that are essentially up to quasi-finite maps, are essentially period maps that appear on the boundary of my original log smooth base. And if you sort of know a little bit of Hodge theory, I can tell you that what period maps are these? Well, these are exactly the ones associated to the associated graded of the limit mix Hodge structure. So sort of on strata in the boundary, these give you new variations of Hodge structures that are capturing sort of the pure part of the degeneration of the Hodge structure. And each of those period maps you can take its image, and that's somehow it gives you the stratification of this Bailey-Borel compactification, again, up to quasi-finite maps. So there's a little bit of a subtlety there. And okay, so there's lots of previous work on the circle of ideas by Green, Griffiths, Laza, and Robles recently, and Green, Griffiths, and Robles, and they do some special cases, including the case when the base y is two-dimensional. Importantly, Green, Griffiths, Robles establish a theorem that we use in our proof, and I'll say more about that when we come to it. Okay, so any questions about the
Can you just
theorem?
go back to the
Yeah, the previous slide.
um just trying to understand sort of the conclusion of theorem one. So
Yeah.
so By, this is a subalgebra of the section ring of Ly, and so it's a finitely
Correct.
generated. You're saying it's a finitely generated subalgebra. So do you know anything like, is the larger algebra like an integral over the smaller one, or is the space of, you're calling the moderate growth sections, like, is this, does this come from some sort of divisor
Hey,
related to Ly or anything like that?
yeah,
Or
yeah, good question. So let me say a couple things. So first of all, so Y is the reason I'm writing it this way is so it's super canonical, but Y is not proper. So this, if I didn't have the MG, this full section ring would be huge. Like that, each individual term wouldn't be finitely generated.
I was proper already. Okay, that helps first of all. Yep.
Okay, so this Y is like the image of this period map, which is not proper. And so you impose this moderate growth condition to get a finite dimensional space of sections in each graded piece. Okay, so even before you ask if it's finally generated as a graded ring, you had better have each graded piece be finite dimensional. Now, but this might make you happier. So this Y, remember, was the image of the period map, right? So now you can take some resolution of it. Let's call it X, or let's call it X minus D suggestively, and you can take in a log smooth convectification of that, so embedded inside some X. Okay. Now we have this line bundle Ly down here, which you can then just pull back to X minus D. Sorry. And like I've been saying before, you have Hodge theory supplies you with a natural way to extend the line bundle, this Griffiths bundle, in the log smooth situation. So you get this natural line bundle Lx on X. Okay. Now this line, so the sections that I'm calling moderate growth sections of Ly are precisely the sections which, if you pull them back to a resolution, extend to this natural extension. Okay, so that's an easy way to see that the space of moderate growth sections is finite dimensional. They're precisely the sections that will extend on any log smooth convectification of a resolution. And then
So
then I have a proper
is it
variety.
wrong to sort of think about it like as a forced sort of retie type of construction for the canonical sort of singularities? Does that make sense?
It might make sense, but I'm not familiar with it, but it
Okay,
might.
okay.
Yeah. Somehow I'm writing it this way because I don't want to reference like a particular convectification or a particular resolution or anything like that. And so this is the most intrinsic way to pick out this space of sections. But then again, for any log smooth compactification of a resolution, it just ends up being the actual section ring of the natural extension of this line bundle. Does that make sense? Yeah. Okay. Great. Okay. So where was I? Oh, I was here. Okay. So I mentioned quite a ways back that this Griffiths bundle kind of shows up naturally. Where did this first show up? I guess here. This Griffiths bundle naturally shows up because it's the bundle you expect to be ample because of curvature reasons. So this line bundle comes with a Hodge metric, which, if you do some computations on the period domain, you find out that its curvature form is positive definite. That's why you expect it to be ample. But there's lots of other semi-positive line bundles floating around in Hodge theory. So for instance, you could look at a variation of Hodge structure on the complement of an S and C divisor. Okay, so again, so W is a local system and F dot W is a filtration on the associated flat vector bundle that satisfies some properties. And let's look at those variations of Hodge structures for which the deepest piece of the filtration is a line bundle. Okay. And in this situation, I'll call that the Hodge bundle. Okay, so we had the Griffiths bundle, which we could form for any variation of Hodge structure. We tensor the determinant of all the filtration pieces together. The Hodge bundle is just going to be the deepest piece of the filtration in the particular case when it is a line bundle. And if that is the case, if the deepest piece of the filtration is a line bundle, we'll call that a Calabi-Yau variation of Hodge structures. Okay, so there's a reason for that, and that is if we take a smooth projective family of Calabi-Yau M folds, okay, so these are varieties whose m-dimensional smooth varieties whose canonical bundle is trivial. And that means that the variation of Hodge structures I get by considering the middle cohomology of those Calabi-Yaus is a Calabi-Yau variation of Hodge structures in this sense. And that's just because the canonical bundle, I mean, the deepest part of the Hodge filtration here is just the push forward of the relative canonical bundle. Okay, so if it's on fibers, if it's trivial, then this will give me a line bundle. Okay, so that's the Hodge bundle. And yeah, so I just write that here. That's what this Hodge bundle is. Okay, it's the push forward of the relative dualizing sheaf. And okay, so it's a piece of it's a piece of the Hodge filtration. It turns out those are all semi-positive. Okay, they're not positive definite, but they have metrics with semi-positive curvature. You could ask, is it semi-ample for an abstract Calabi-Yau variation of Hodge structures? This is kind of a greedy question you could ask. And the answer is not always. Actually, it's quite subtle. I can give you an example maybe after the talk or whatever, if there's time left over, give you an easy example of when this is not true. Nonetheless, there are important cases for when we want to know the semi-ampleness of such line bundles. Principally because, the Griffiths bundle appears naturally in Hodge theory, but geometrically it's kind of a weird object to consider. You have a family of varieties, you look at the you look at the tensor of the determinant of all the Hodge filtration pieces, you get some positivity result there. But geometrically, it's much more natural to be able to say something about this relative canonical bundle. Okay. Great. Now the trick we can use within the world of Hodge theory is that if I take any variation of Hodge structures, variations of Hodge structures form like a tensor category. So I can take the wedge to the rank FP of that variation. That's still a variation. And this is a Calabi-Yau variation because its deepest filtration piece is just the determinant of FP, which is going to be a line. And then the tensor of a variation will also be a variation. And the deepest piece of this tensor will just be the tensor of the determinants of the filtration pieces. Okay? So this is a bit of a sneak, but the point is that given any variation of Hodge structures, I can always build a Calabi-Yau variation whose Hodge bundle is the Griffiths bundle of the original one. This always confuses people when I say this, and maybe I should stop saying this in talks, but it's important to how we actually prove things because we need to what we end up proving is about Calabi-Yau variations of Hodge structures, but it applies to all variations of Hodge structures, and that's because there's this construction, this wedge and then tensor, whereby you can take any variation and produce a Calabi-Yau one. So this is a polarizable Z variation of Hodge structures whose Hodge bundle is the Griffiths bundle of the original thing. Okay, so if we can prove something about Hodge bundles being semi-ample, then we will secretly be proving that Griffiths bundles are semi-ample. But we'll be proving a more general theorem, right? Because it's not true, but if I were able to prove that for any Calabi-Yau variation of Hodge structure, the Hodge bundle is semi-ample, that would in particular prove that the Griffiths bundle is always semi-ample. Okay, so this brings me to the same main theorem. It's not that literal statement I just made, because that's not true, but it's a qualified version of that. Okay, so here's the theorem. This is again with Stefano, Mirko, and Jacob. Okay, so let X comma D be a proper log smooth algebraic space. Doesn't really matter. It can be a projective, a smooth projective variety with an SNC divisor. And take a polarizable now Calabi-Yau integral variation of Hodge structure on the complement of the log smooth divisor. Okay, so that again, that means that the deepest piece of the filtration is one-dimensional. So I can talk about the Hodge bundle. And the two conditions I need to assume are that the Hodge bundle is integrable and that it has torsion combinatorial monodromy. Okay, so these are two conditions, which I'll talk about in a second. And subject to these two conditions, the Hodge bundle is semiample. Okay, so that's the theorem. Like that gives us a very general criterion for when the Hodge bundle in a Calabi-Yau variation of Hodge structure is semiample. And it's actually if and only if. Probably should have said it in this theorem. Both these conditions are also necessary. So the theorem is saying they're sufficient. Okay, so let me tell you what these two conditions are. They're not so bad. So integrability, okay, it's an integrability type condition, and this is what it is. So this Hodge bundle MX sits inside of a local in a flat vector bundle. Okay, so it makes sense to say that that the Hodge bundle is flat. I just mean with respect to the connection on the ambient flat vector bundle. Okay, and the integrability condition is if this line bundle is ever flat on some analytic germ, then it's actually flat on the Zariski closure. Okay, so this is some strong algebraic integrability about the sort of foliation. It's not really a foliation, but sort of the analytic subs along which, no, well, it is a foliation, along which this MX is flat. Okay, and it says that those leaves are always algebraic. Okay, so that's that's the integrability condition. And remember, from any variation of Hodge structure, I can produce a Calabi-Yau one whose Hodge bundle is the Griffiths bundle of the original variation. So by proving stuff about Calabi-Yau variations and their Hodge bundles, we're secretly proving stuff about Griffiths bundles. And whenever we do that construction, this integrability condition is automatically satisfied for the Griffiths bundle. Okay, so if we care about applying this theorem to the case of the Griffiths bundle, this integrability condition will always be true. Okay, it's not true for Hodge bundles in general, for any Calabi-Yau variation, but for those Calabi-Yau variations that arise from that wedge and tensor trick, it is true. Second, there's this torsion combinatorial monodromy condition. What does that say? Well, again, it's actually a pretty simple condition. It says that if this line bundle is numerically trivial on a connected curve, then it's in fact torsion. Okay. So let me just draw a picture. So what this means, you might have some like nodal curve living in the base, living inside of X. Okay, and if MX is numerically trivial, excuse me. Well, Hodge theory tells you that if MX is numerically trivial, then on each component, it's torsion. Okay, that's something that Hodge theory gives you. So that's why this is called torsion combinatorial monodromy, because it's saying that the combinatorial sort of part of the monodromy of this line bundle is finite. Okay, so on each component it's torsion, and that means that I can sort of I can there's a natural connection on this line bundle on this reducible curve, and I require that as you go around that the monodromy ends up being finite. Okay. And importantly, okay, so this is the result of Green, Griffiths, and Robles that we use. Again, if you do this wedge tensor trick and thereby reduce the Griffiths bundle case to the Hodge bundle case, it turns out that the Griffiths bundle always has torsion combinatorial monodromy. Okay, so the upshot of this trick, of this wedge tensor trick, is that this theorem implies, or doesn't imply, but implies a large part of theorem one because the Griffiths bundle, when you do that tensor wedge, the Griffiths bundle is automatically integrable and has torsion combinatorial monodromy, and therefore you conclude that it's semi-ample. But this theorem applies to strictly in strictly more cases because it applies to Hodge bundles in general. Again, that's always confusing when I give this talk. I don't know, I need to find a better way to say it. But this theorem 2 sort of applies to more circumstances, and it's going to apply geometrically in a circumstance that we can't apply theorem 1. Maybe it'll become clear when we get to that. And I'm going to get to it now. So this brings us to B semi-ampleness, because B semi-ampleness is exactly a statement about the semi-ampleness of a Hodge bundle. Okay, so let me just refresh our memories a little bit about what B semi-ampleness is. Okay, well, let me state the theorem first, I guess. So if x comma d, so now we have a pretty general theorem about when the Hodge bundle is semi-ample, subject to 2 conditions. Okay, so theorem 3 is going to tell us in a certain geometric setting, those conditions are always satisfied. So if x comma d is a proper log smooth pair, and suppose we have a polarizable Calabi-Yau variation of Hodge structures on the complement of the SNC divisor, coming from the middle cohomology of a family of KLT Calabi-Yau pairs. Okay, so this isn't now some abstract Calabi-Yau variation of Hodge structures. This is one of a very particular type. I take a family of KLT Calabi-Yau pairs and I look at their middle cohomology. And the theorem is that in this situation, the Hodge bundle is both integrable and has torsion combinatorial monodromy. Okay, those are the 2 conditions that we had in the previous theorem. So as a consequence, we're going to be able to get some semi-ampleness about the Hodge bundle. Okay, and this is what gives you the B semi-ampleness conjecture. So let me just say a few words about what that means. I'm sure there are people in the audience who actually know this stuff better than I do, but let me do my best. So let's take an LC pair and take a fibration, which is sort of log k trivial in the sense that kz plus delta is pulled back from something on x. It's sort of relatively linearly equivalent to 0. Okay, so that means that the sort of fibers are like log Calabi-Yaus. And in this setting, there's a canonical bundle formula due, originally due to Kodaira for the case of elliptic fibrations, but then generalized by Kawamata and Fujino and Mori and Kolar and many others, which gives you that kz plus delta is the pullback of something. It gives you a particular way of decomposing the something it's a pullback of. There's the canonical bundle of the base itself. There's what I'm calling mx suggestively, which is the moduli part. And then there's a boundary part, which is sort of measuring the singularities in the fibers. Okay. And the B semi-ampleness conjecture is that this mx is B semi-ample, which essentially means that if you go to a nice enough model, that this moduli part is semi-ample. And if you go to a nice enough model, this moduli part is exactly the Hodge theoretic extension of the Hodge bundle of the variation of Hodge structures you get on the open part by considering the sort of general fiber. So that's why I'm using the same notation, and that's why it's a corollary of this theorem. Once you have this theorem that tells you that in this situation, the Hodge bundle satisfies the 2 conditions you need in order from the previous theorem to conclude that it's semi-ample, you can deduce this semi-ampleness. Okay, so this conjecture was formulated. Sort of, it goes back to the work of Mori and then Kawamata and Shakurov and Ambro, and then ultimately, sort of the version stated here is due to Prokhorov and Shakurov. And there have been some past results by Ambro and Lazic and Flores, and again many others. I'm not going to be able to list all of them. But a nice corollary to keep in your mind, and this is, to experts, it was clear that this was sort of equivalent, is that, we started this story talking about the Bailey-Borel compactification of AG, the moduli space of principally polarized abelian varieties. The sort of upshot here is that if you take a moduli stack of polarized KLT Calabi-Yau pairs, but if you like, for simplicity, just think about a moduli stack of smooth polarized Calabi-Yau varieties. Those moduli stacks have canonical Bailey-Borel compactifications up to taking the core space. Their core spaces have canonical Bailey-Borel compactifications. Okay, so just as AG, which is a moduli space of Calabi-Yau varieties, because abelian varieties are Calabi-Yaus. So AG has a Bailey-Borel compactification. So any moduli space of Calabi-Yau varieties has a Bailey-Borel compactification, and the Hodge bundle, that naturally lives on that moduli stack, extends and has all the nice properties that it ought to have on a Bailey-Borel compactification. Okay, great. Okay, so let's describe a little bit about the proof of this theorem too. Okay, so theorem one, like I said, like the main step in theorem one is this theorem two. There's some other work you have to do that I don't want to get into. But for the semi-ampleness part of theorem one, and for the B semi-ampleness conjecture, it's sort of this theorem two. That's the main thing. You want to prove in this situation of a Calabi-Yau variation of Hodge structure, if you have these two conditions, that the Hodge bundle is semi-ample. Okay, so semi-ampleness is hard because there aren't any super great criteria for when something is semi-ample. Like for ampleness, there's many good criteria. There's even a numerical criterion by Nakai-Moishe zone. Semi-ampleness is much trickier because somehow you have to be able to distinguish, it's not numerical. You have to be able to distinguish between, degree 0 line bundles that are torsion and ones that aren't torsion. So that's tricky. So how does one prove semi-ampleness? Well, if you have a variety X with a line bundle L, one way to prove semi-ampleness of the line bundle L is to construct some topological space that it maps to Y, which you then somehow as a guiding star, you want to take the fact that if you're a semi-ample line bundle, that means you're pulled back along an algebraic map from an ample line bundle. So you want to construct that image variety and the ample bundle on it. So you start with X. You first make it what should be the topological space underlying that variety Y. Then you equip it with an algebraic structure in such a way that the line bundle L descends to some Ly. And then once you've built this image variety together with the descent of the line bundle, now it ought to be ample down here, and so then you prove the ampleness there. Okay, that's just a rough sketch. So basically what I'm saying is if you're asked to prove the semi-ampleness of a line bundle, you can try to produce the contraction that it will induce and thereby and then reduce it to proving the ampleness of a line bundle, which is easier. Okay, so that's the strategy we're going to take. So we're first going to make this contraction that the line bundle should induce as a topological space. Okay? Now, that's not so bad because you know exactly what has to be contracted, right? I mean, if you have a line bundle on X, and if L is supposed to be semi-ample, then it has to contract exactly the curves that are degree 0. Okay? So we can define an equivalence relation on X, which is just being connected by chains of curves that are degree 0 with respect to that line bundle. Okay? Now, that's not clearly, this is something that people have thought about before to define like Neff reductions of Neff line bundles and things like that, or the MRC quotient or things like this. This is not necessarily a super well-behaved equivalence relation. So the first thing you have to do, and this uses the fact that this R is coming from Hodge theory, right? That it's using the fact that there's a Hodge that MX is a Hodge bundle. You have to show that this equivalence relation is in fact a proper algebraic equivalence relation. Okay. Okay, so that's not so hard though. So you prove that. And once you prove that, then that means that this is a reasonable topological space. At the very least, you can form this topological space. Okay, like it's a Hausdorff topological space. So that's a solid step in the forward direction. We've produced what should be the image of the contraction that the line bundle produces. Now we actually get a little bit more, and that's using this older theorem that I mentioned about the image of a period maps being algebraic. Okay, and what that basically means is if you take the natural stratification of this log smooth x comma d, then it descends to y. Okay, so that you can produce a stratification of y such that the inverse images of the strata, I'll call them y sub s, are just unions of strata on X. And like I said, by that older theorem about the algebraicity of images of period maps, each of these strata is algebraic because each of them is an image of a period map, and this Hodge bundle descends on each of them as an ample line bundle. Okay, so somehow you can imagine you have XX with its log smooth divisor. It has this line bundle, and you can kind of separate all the strata out. And on each one individually, you can look at the image of the period map. You get something algebraic. That's what this y sub s is. And the Hodge bundle descends because it's the variation that's pulled back. And the Hodge bundle is ample on the image there. Okay. So what it remains to do is take all of those pieces of that stratification, all these YS's, and just reassemble them into this Bailey-Borel compactification. That's the tricky part. Okay. So here to get both this descent and to get the ampleness, we've used both of the conditions. I won't get into where and why. I mean, you can see that the torsion monodromy, combinatorial monodromy is already kind of necessary to get the line bundle to descend, because there could be like one of these chains of curves where you have infinite monodromy in a fiber, and then there's no way the line bundle is going to descend. So somehow we've used torsion combinatorial monodromy to get the descent, and then to get that it's ample downstairs, we've used the inevitability. But anyway, let me ignore that for now. Okay, so what's the situation we're in? Okay, I don't want to get into this actually, but maybe I'll just draw a picture. I'll draw the picture I usually draw when I'm doing this in person. So we've given, like I've said, we've produced this topological space downstairs. You know, we have X mapping to Y. Okay, this Y. Y is a topological space, and we've produced a stratification of Y. And on each piece, we can algebraize. We can give it an algebraic structure, and we can descend the line bundle such that it's ample. We just got to glue all these things back together. Okay, so what does it mean to glue them back together? Well, it means we need to make sections. Let me draw a picture like this. So suppose this is X, okay, and suppose here's the divisor sitting inside of X. Maybe it looks like this. Okay, and it's mapping down to Y. And maybe I should use some different colors actually. So here's one divisor. Maybe here's another divisor. Okay, and all the green stuff, let's say, gets contracted to a point, and let's say all the red stuff gets contracted to this line. Okay, and we have this line bundle. Why it's doing that? We have a line bundle on up here, which descends to Y, and so we want to give an analytic structure to this space, which means we want to produce local functions. And the only way we have of doing that is like locally around any point downstairs, we want to produce sections of this line bundle on the inverse image. Okay, so like for any, for any point in any neighborhood, well, that's an awful color. We want to look at the pre-image that gives us this little neighborhood, and we want to construct sections in that pre-image that separate points, right? We need to be able to produce functions that separate points to give it an analytic structure, and we do this via this line bundle here. So we need to locally downstairs, locally down here, we want to produce sections on pre-images that separate points, okay? So, okay, I don't want to go through all this. Yeah, okay. So let me describe it a picture, and then we'll have the text. The upshot, I'm not going to go through this, but the upshot here is that you can let me just say it in words. Sorry, that's a little confusing. You can make let me step two. Let me tell you what the product of step two is. you can make sections locally on any stratum which separate points on that stratum. Because that's important. Okay, so that's what you do some delicate Hodge theory, and you show that you can make sections locally on any stratum that separate points on that stratum. Okay, so let me just draw some pictures now. So let's go back to this is my picture of Y. And remember, it has its stratification into pieces like this. Okay, let me draw a few versions of this. Okay, so these are all pictures of the same thing. These are all copies of Y. Let me draw one more maybe. Okay, and I'm gonna draw some scenarios where you might want to try to generate functions that locally separate points. So you might want to take a neighborhood like here and separate 2 points in there. Okay, this is okay, right? Because we know that this open part, this open stratum, each stratum is algebraic, right? So this biggest stratum is algebraic, so we can in particular we can find sections of the line, and the line bundle is ample, so we can find sections of the line bundle that separate these 2 points. That's no problem. What else can we do? Well, in a neighborhood like this, we can find sections that separate points on that stratum, right? That's the content of this step 2 that I didn't describe how it works, but I'm telling you that we can do that. Okay, so what is the issue? The issue is we can't do something like this. We can't look at a neighborhood, like a small neighborhood of this red stratum, but separate points that are not on that stratum. Okay, so that's an issue. And you can see kind of what the problem is. I mean, by what we have over here, if you further zoom in to a smaller neighborhood of those 2 points, you can find a local section that separates those points. But we don't know that such sections can be glued up into a full neighborhood of this red stratum. And the kind of local topology around this red stratum can be quite complicated. Okay, so this condition of sections gluing up, I mean, we all know that sort of the Bailey-Borel singularities can be quite bad. So these sections glowing up in the neighborhood of even locally and in sort of on the complement of the boundary in the neighborhood is a very non-trivial condition. Okay, so this we can't do. So this we could do, this we could do, this we can't do. Okay, so we need to prove something in order to be able to do that. And this is where sort of an inductive argument comes in. And here's sort of the key point. Okay, so let me introduce some terminology. So let y less than or equal to I be the union of the codimension less than or equal to I strata. Okay. So like y, so in this notation, this biggest one is y less than or equal to 0 is the complement of the boundary. Y bigger than or equal to 1 includes the red line, and then y bigger than or equal to 2 includes the green line too. So it's a strictly increasing sequence of open subs. Okay, so the problem is that local sections from step 2 do not give y an analytic structure. This is what I was saying over here, right? Because we can't have an analytic structure, you have to locally have sections that separate points. This scenario is problematic. But we can, so we're going to do an induction where we inductively assume that not only have we algebraized y less than or equal to I, but we assume that global sections of the line bundle separate fibers. Okay, so that's a key point. So not local sections of the line bundle, but in fact, global sections of this line bundle. So that's why we need to algebraize as we go. Okay, we're going to, as we we start from the biggest stratum, we start adding strata of starting with the biggest dimensional one and then the next biggest dimensional one and so on and so forth. And in each step, we're going to algebraize it, and we're going to prove that global sections of the line bundle separate fibers. And that's 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 how to say, that's good news. So if we can do that, that's good news because that fixes this problem, right? Because if we've algebraized how to say, so because this biggest stratum is algebraic, we have global sections that separate these 2 points, and so that actually fixes this problem. Sorry, I'm not describing this very well. So this is actually okay, but only because y0 is algebraic. Okay, and then the issue is that we were faced with a similar issue if I go to the next stratum down. Okay, so sorry, so I think I'm somehow this is hard to convey over slides, but the point is that having these local sections from step 2, let me just do the first step of the induction. So you start off with y less than or equal to 0. That's the biggest stratum. That we know is algebraic by the theorem with BBT. We also know from that theorem that global sections of the line bundle separate points. So that means we can actually give an analytic structure to y less than or equal to 1. Okay, so if I just add that first stratum in, then by the pictures I was drawing over here, all 3 of these scenarios are okay. So we can make an analytic structure here. So this has an analytic structure. This is analytic. But even better than that, it's definable analytic. So I'm not going to get into what definable means, but this is some tameness hypotheses on functions. So this is some sort of a tame analytic variety for which there's a definable gaga, and that implies that it's algebraic. Okay, and as soon as y less than or equal to 1 is algebraic, we also get that global sections of the line bundle separate points on y less than or equal to 1. And those global sections solve this problem of not knowing that you can piece together sections locally. Because global sort of Zariski open sets are very big compared to analytic open sets. Sorry, I don't think I described that very well, but that's because
Can I ask a question? So
yeah, please do. Please do,
okay,
yeah.
so in the end, is Y a bona fide projective algebraic variety, or is it some form of
Absolutely.
stack? It's a bona fide. Okay, and
Bona
then
fide. Yep.
so then can you keep track of the subvarieties of X that are contracted by MX?
You can keep track of them in the sense that so on X, so remember X comma D is like the log smooth thing, yeah? And if you were to give me complete information on each stratum of what the like limit mixed Hodge structure looks like, I could tell you which ones get contracted to which ones.
So that's very interesting. I mean, so you might be familiar with like the Sean-Keel endowed with a map formalism. So
Mhm.
I'm wondering if that picture is sort of seen in this setup.
Oh, that's a good question. Yeah, so remind me, I vaguely remember this. So how does that work again?
We'll give sort of the definition wrong, but roughly speaking, when you have what he calls endowed with a map, then you can characterize semi-ampleness in terms of keeping track of sort of the dimensions of contractions in the way that you would sort of want it to hope for. So then sort of the issue is, in some sense, so how do you produce an endowed with the map condition? Is that sort of condition somehow checkable? And so that's sort of the issue that you seem to be sort of doing, in your proof in some sense. And so I'm just sort of wondering if your proof is sort of quite literally you're creating a map. And so then somehow then reverse engineer. I mean, if you can sort of somehow see that, that's sort of, I mean, that's kind of the sense for my thoughts.
Oh,
If
that's
that, if
interesting.
that,
Yeah. So I guess I was thinking about something else. I didn't know about this.
I
I'll
mean,
look
he's
into
doing
that.
this
That's
in
very interesting.
characteristic P primarily, but I mean,
Yeah.
the conclusions are still, I mean, work in characteristic zero more.
No, yeah,
Yeah.
that's very interesting. That's exactly the kind of thing we're using. So I wonder if, yeah, I'll have to look into that and see if that is in fact what we're doing. Because we are using the fact that we can, you have this map floating around. I mean, you can make this map, and so maybe that is the extra structure that he wants. Other questions? Okay, so yeah, I think that the picture I was trying to paint got a little confusing at the end, but just to kind of because I want to get to the birational geometry a little bit, but just to give you the upshot, the point is that you make this target space, you stratify it, you know in all the strata it's algebraic with an ample line bundle. You want to do this gluing. We prove in the old paper that you can, in fact, not only is each stratum algebraic, but um, points are separated by global sections of the line bundle, which is good. And what this allows you to do is in each, starting with the biggest stratum, which you know is algebraic by the old theorem, you can add in the next biggest stratum. Then you know that there are global sections that separate points. That means you can equip it with a definable analytic structure, and therefore an algebraic structure, and therefore know that global sections separate points on this bigger, on the union of the biggest strata and the next biggest strata. And so now you can continue. Okay, and so the reason the use of O minimal gaga is key is because we have to algebraize a non-proper variety at each point. So we can't appeal to normal gaga. So that's the point I want to emphasize. Okay, great. So now in the last little bit, let's talk a little bit about um, this theorem 3 that I mentioned, which tells you that these two conditions, so let's just refresh our memories about theorem 2, which luckily I have right here. Theorem 2, it gives us a general semi-ampleness result, assuming these two conditions. This integrability and this torsion combinatorial monodromy. And we know that when we want to apply this theorem to the Griffiths bundle, those two conditions are always satisfied because integrability is obvious, and the torsion combinatorial monodromy is a theorem of Green, Griffiths, and Robles. And okay, so what about the case when we have that's relevant to B semi-ampleness? What about when we have a family of Calabi-Yau varieties? Okay, so that's what theorem 3 is. Theorem 3 tells us that if you have a proper log smooth base and you have a Calabi-Yau variation of Hodge structures that comes from the middle cohomology of a family of KLT Calabi-Yau pairs, then the Hodge bundle is integrable and has torsion combinatorial monodromy. Okay, so this is not automatic at all. It's not like the Griffiths bundle. And it's not some abstract Hodge theoretic thing. This is really going to use the geometry of the family. This is going to use some birational geometry. So let's talk a little bit about how the proof of that is going to work. Okay, so we have an LC fibration, and the kind of key point is to look at the minimal LC centers, which dominate X. Okay. The point of that is that the sort of the smallest piece of the variation of Hodge structure that contains the Hodge bundle is going to be carried geometrically by this minimal LC center. So the picture I always like to keep in the back of my head is if you think of a degeneration of, so K3s are Calabi-Yau. If you take a degeneration of a K3, one possible type of a degeneration of a K3 are these sort of type 2 degenerations, which are like chains. You start with or let's just say there are two rational, well, it's a chain, you start with a rational surface at one end and a rational surface at the other, and it's a chain of ruled surfaces over elliptic curves between them. Okay, so in other words, I mean, for instance, I could have two rational surfaces that are glued along an elliptic curve, or I could have two rational surfaces and a ruled surface over an elliptic curve, where I glue one of the rational surfaces to it along one section and the other one along a different section. So they're glued along elliptic curves. So the point in this picture, so I guess I can draw the picture while I was doing it with my hands. So the picture I like to keep in my head is, you sort of maybe you have a K3 surface. This is a K3, and the kind of thing it degenerates to is you have a rational surface, and maybe an elliptic curve here, an elliptic curve here, and you have like a chain of ruled surfaces over elliptic curves. That's the kind of degeneration that shows up. Okay, so what is the source in this situation? The minimal LC centers are these elliptic curves that show up. Okay, and indeed, in the limit mixed Hodge structure that shows up here, you get the Hodge structure of an elliptic curve showing up. and that is this elliptic curve. Okay, so it sort of carries this minimal LC center geometrically is carrying the sort of part of the Hodge structure that has the Hodge bundle in it. And this works in the boundary well, as I was just demonstrating. I mean, the whole point is that this description works even as you start degenerating, assuming you sort of go to a good enough model. So let's first talk about the integrability. This is basically a result of Ambrose. So remember, what does the integrability say? It says that if along an analytic germ, the Hodge bundle is flat, then the Hodge bundle is flat on its Zariski closure. Okay. And the point here is that for Calabi-Yau pairs, the period, I mean, with some subtleties, for Calabi-Yau pairs, the period map of the Hodge bundle, all right? So if you look at the period map of the variation of Hodge structure and just look at the Kodaira-Spencer map on the first part, that gives you an immersive map. It's immersive if you just look at the Hodge bundle. Okay, and so then the point now is that if you have an analytic germ along which the Hodge bundle is flat, that implies that the source is varying isotrivially. Okay, so the family of sources that you get on that germ is trivial. Okay, but the locus along which the source is trivial is an algebraic locus. So therefore, it must also be the source must also be varying trivially on this Zariski closure of that germ. Okay, so that's the integrability condition. Okay, and I'm just spelling it out here. Okay, so it follows from the Kodaira-Spencer map on the deformation space being immersive. Okay, so the tricky one, the one that actually requires a little more argument, is the torsion combinatorial monodromy. And the essential issue, I'd like to draw a picture here, is that the source is not unique. Okay, so let me draw a picture. And so torsion combinatorial monodromy, remember, is about I have a reducible curve, so like a chain. Let's talk about a nodal loop of curves. And I want to know such that the Hodge bundle is degree 0 on all of the components. And I want to know that the monodromy around this loop is finite. Okay, so let's actually unpack what that means. So suppose we have two curves meeting at a node. Okay, and this is living somewhere in the base X, so there's some possibly degenerate family of Calabi-Yaus sitting above it. And let's say the family of Calabi-Yaus on this right curve maybe looks like this. I don't know, something like this. Let's say it has two components and they meet along something. And let's say along this, it looks like this. Okay, so these are like two surfaces like meeting at a curve. So as I was explaining before, let's say that the where they meet, this curve they're meeting at, let's say, is the minimal LC center for on this left curve, and over here, let's say it's this. Okay. So now as you degenerate, you can't be degenerating too violently because the Hodge bundle is degree 0 on each of these curves, but it could still be the case that the special fiber looks something like this. Okay, so I get something that looks like this, and the limit of the green thing is like there, and the limit of the red thing is there. Okay, so this is what I meant by the source not being unique, right? We like along this curve, maybe our family looks like nice and kind of topologically locally trivial, and I can follow this green source along, right? And that's carrying this piece of the variation of Hodge structure that I care about. And maybe along this curve, the same thing is true about the family above it, right? It has some general shape, and this red source I can follow along. But as I pass to this node, maybe the limit of this source is one source, and the limit of this green source from the other one is this other source, right? So there are two sources now on this fiber over the node. Okay, so there's no reason the source has to be unique. And in fact, that K3 example I gave you, there were three sources. Sorry, source is the same as minimal LC center. So I need to somehow, so what is the Hodge bundle? The Hodge bundle is just the space of top dimensional forms on this source, okay, on the red one here or the green one here. And I need to understand how I should be identifying the space of top forms on the green thing and the space of top forms on the red thing, right? that the identification between those two vector spaces is how I compute the monodromy as I go through this node. And then I do it again at the next node and the next one. And then I go all the way around and I compare the difference. Okay, and so this is where, well, it's going to erase my picture as soon as I um, um, go to it. So let me go to it first and then I'll go back. So the key is Kolar's P1 linking, right? So Kolar's P1 linking tells you that between adjacent sources, if you go up one dimension higher, there's a P1 ruling, which means that the green source and the red source are identified via a birational map. Okay, that's what I'm saying here. Okay, well, this birational map, so then we need to answer the question of how are the spaces of top-dimensional forms related under a birational map? Well, now we use the finiteness of canonical representations. All right, so the image of the group of birational maps from S1 to S2 inside of HOMs between the spaces of top forms is finite. Okay, so the number of the ways I have of identifying these two things lives in some finite thing, and so as I go all the way around and I keep at each node identifying by these birational maps, when I come back around, it has finite monodromy. Okay, and so that's how you prove the torsion combinatorial monodromy. So that's all I wanted to say. So yeah, let me leave the last 10 minutes for maybe questions because I'm sure I went too fast through some stuff.
So thank you, Ben, for your nice talk. Are there any questions or comments? So like in practice, is it hard to compute the Bailey-Borel compactification of the image of the period map? Like, is it hard to compute the graded ring of moderate growth sections?
Well, I mean, I think the answer is yes, but it's quite possible that you would be able to at least get a handle on its points. I mean, this plugs into kind of a long story of people comparing like GIT compactifications to sort of toroidal compactifications in settings where you have your period domain happens to be a locally symmetric variety. And so a lot of those techniques you can imagine applying now that you know that there is some version of the Bailey-Borel, and then understanding the points that you get in terms of sort of what degenerations you allow. So I think the answer to your question is, it's I can't give you a general answer because it depends on the geometry of the particular variety. But for instance, if you're interested in moduli spaces of Calabi-Yau's, for a particular kind of Calabi-Yau, you could in principle understand um, on each boundary component, what the kind of thing you are getting in the image is, because it's sort of related to, I mean, very loosely, and this is something that needs to be fleshed out, but very loosely, if you take a moduli space of Calabi-Yau's and you take the Bailey-Borel compactification that we construct, the strata should essentially be uh, like the should be close to being the moduli spaces of the minimal LC centers for the degenerations. So in the same way that, if you take a moduli space of K3 surfaces, so that ends up being an orthogonal type Shimura variety, and its boundary is a modular curve, which is just the moduli space of the source that you get for the type 2 degeneration that I mentioned, the ones for which there's an elliptic curve popping out. So in the case of moduli of Calabi-Yau's, you should, after understanding what degenerations you get, you should be able to understand what the different strata of the Bailey-Borel are.
Yeah, thank you. So are there any other questions or comments?
Yeah. Hi.
Hey,
Hi. Yeah. I have some question about this technique of using this definable or minimal geometry.
uh-huh.
I'm a bit curious about the step where you conclude that Y is algebraic. You do some induction on strata, and you say each individual strata has an algebraic structure, and then how do you, and then you say y less equal to I as a definable analytic structure, but then how do you conclude that this is algebraic?
Yeah. So I described it really poorly. And that's because, I mean, to be honest, I haven't looked at these slides for a while, and the way I usually give this talk in person is now different from the way I wrote it in these slides, and that's why that's why there started to be a bifurcation in the presentation. So let me try to describe it again very quickly. So again, the situation is you have Y downstairs, and you have this like stratification, and you know that again, I'll just do the first step of the induction, then you'll see how it goes. And you know on each strata that it's algebraic by this Older theorem. And you might maybe you want to know how that's proven. We can discuss that afterwards. But let's take that as a black box right now that just says that each stratum is algebraic. Okay. There's actually more that that theorem tells you, and it is the following that, like for instance, for the biggest stratum, it's algebraic, and its points are separated by global sections of the Hodge bundle, in the sense not global on the stratum, but global on the whole thing. Okay, so like on some resolution of the whole Y. Okay, so there's like an X mapping to this whole Y, which is like a resolution of this Y, and upstairs on X, there are global sections of MX, which lives up here, which separate the points off of the boundary. Okay, great. Okay, and okay, so the first step of the induction is this is what I was trying to allude to, like you know that you can separate points kind of away from the boundary. You know by that step two that I didn't describe, you can separate points on the boundary, and you know also that in a neighborhood of the boundary, you can separate points off the boundary. That's what this extra thing gives you, because you now know that there are global sections of the Hodge bundle that separate points everywhere on the complement of the red thing. Okay, so with these three things, if I can handle all these situations, that means that I can take the union of this biggest stratum and just the next biggest stratum, and this is algebra, and this will have an analytic structure. Okay, are you happy with that?
Uh, is it because this period domain is already analytic? And,
Yeah, well, it's because I have a topological space, and I mean, to be an analytic variety, I just need to be able to produce holomorphic functions locally that separate points. And I've just demonstrated that I can do that because I know this about global sections.
okay.
Okay, so that allows me to glue in this next biggest stratum to get an analytic variety. Okay, now if I don't use any definable machinery, I'd be stuck, because now I have a non-proper analytic variety, and there's basically no hope of algebraizing that.
Yeah.
But this is not just an analytic variety. It's a definable analytic variety, which means that the sort of analytic structure has some tameness properties that in particular means that O minimal Gaga applies, which tells me that in fact, I mean, one of the things we prove is that if you have a definable analytic variety that is the image of an algebraic variety, then it itself is algebraic. So that's the situation here. You have an algebraic variety that's mapping down to this definable analytic variety, and that shows that it's algebraic. So now you know that the sort of purple union red is algebraic. And so the inductive step is that now you've learned something stronger. You've learned that global sections of MX separate points on both the purple thing and the red thing, which means that I can now go one step further, because now I can separate points in a neighborhood here, like that, if that makes sense. So I can add in the next stratum, basically.
But can you separate points from different strata?
So like as you go, you're going to be proving that. Like you don't go in knowing that, but as you algebraize bigger and bigger unions of strata, you will eventually be showing that you'll be able to separate those points. Yeah.
Okay.
Yeah, it's a bit, yeah, it's a bit small. Yeah, it's hard, it's hard to communicate over Zoom, but hopefully that makes some sense.
Yeah. Thank you.
Okay, so are there any other questions? Okay, if not, then let's thank Bang again. Yeah. So thank you very much for coming
No,
today.
sure. Thank you. Yeah.
Yeah. Well, we'll see you in April.
Yeah.
Yeah.
Looking forward to it. All right.
Yeah. Yeah.
Bye.
Bye.